important because your excuse me, your next homework assignment will be implementing the graph ADT using parametric polymorphism, right? Also known as generic. All right, so I will post their solutions to the back test probably tomorrow morning, so that if you have your own solutions, you can verify them. All right, and yeah, don't forget that the homework is still out there, so the homework is pending. So hopefully you already started. If not, it's a good time to start. So I think out of the remaining homework assignments, this homework 5 is the hardest one, right? It will probably take you longer than homework 6 or homework 7. Right? So make sure you allocate enough time. That's why we give you more time. Homework 6 and homework 7, it's going to be just 1 week for each, right? Because we are getting close to the end of the semester. All right, so let's start with our new topic, and we need to talk about polymorphism. It turns out that there are different flavors of polymorphism. One is called ad hoc polymorphism. Another one is called subtype polymorphism, and the third one is called parametric polymorphism. Parametric polymorphism is generics. This is our next topic. But the first two types, the first two flavors of polymorphism, we have already experienced. So subtype polymorphism, right? Earlier, when you were introduced to the object-oriented paradigm, right? You learned that there are those fundamental concepts behind the object-oriented programming, encapsulation, inheritance, and polymorphism. So, that path, you could just say polymorphism, right, without adding any qualifier. Just say polymorphism. And by polymorphism, then what you actually meant was subtype polymorphism. So, subtype polymorphism is the ability of an object in a sense, to represent not just itself, but also an object of any subtype. That's why it's called subtype polymorphism. So we should be somewhat familiar with the concept. We are going to look into it deeper because behind the concept of subtype polymorphism is the same idea that we discussed before, the idea of substitution. Right? So it is important for us to know when we are allowed, when it is safe to substitute one object for another, or one method for another. And the reason we care about substitution, again, this is like the silver lining that runs throughout our entire course, is reasoning about the correctness of code. So if we are able to come up with some rules that say, well, if you perform this substitution, it is safe, it is valid, it does not break the correctness of the code, that's a very useful result, because then we know, okay, I proved that this method is correct by using the reasoning techniques that we discussed before, and then if I just substitute it with another method subject to a set of rules, then I don't even have to prove that this method also works correctly. It will, right? Because it is a safe substitution. So this is basically what Liskov substitution principle, LSP, is about. All right, and then the third type of polymorphism is called ad hoc polymorphism, and this is something that you are actually familiar with already, but maybe you just didn't know that it is called ad hoc polymorphism. Right? So ad hoc polymorphism is the overloading. Right? So here are the three types: ad hoc, which is overloading; parametric, which is templates in C++, generics in Java; and subtype polymorphism, which is the subject of our topic today. All right, so this slide we have already seen before. Right? This is a side-by-side comparison of overloading with overriding. So overloading, we have two or more methods that have the same name. Of course, methods are in the same class. They have the same, methods have the same name, but different parameters. Something has to be different about the parameters. Either the type of parameters, or the order, or the number of parameters, or all of the above in any combination. Something has to be different. The return type is not part of the signature, so the return type does not matter. Overloaded methods cannot differ in just the return, in just the type of the return type of the return type. So overloading, it should be noted that overloading is a compile time concept. So deciding which method to call is this decision is made when the compiler compiles your code. So if you have a find method that takes an int and the find method that takes a string, then at compile time, the compiler will decide which of the overloaded versions of your method is going to call. How is it going to decide? Well, based on the actual arguments that you are calling this find method with. Okay? And then this decision will never be questioned again. Right? Once the overloaded method is decided, this exact method is going to be called, no matter what. Right? So now imagine you have find method that takes a number and find method that takes an integer. Okay? So what would happen if you pass a number to this method? And let's refresh our memory. With the hierarchy of classes that start at number, right? Right, so there's a number class, and then there are double, byte, float, integer, long. So all our boxed numbers, turns out that they are subtypes of number, right? So what happens if you have something like find with a number and find with an integer? Well, first off, and I'm not writing implementations, right? Implementations are immaterial. So first, is this a legal overload? And the answer is yes, because the types of parameters is different. So yeah, it's a valid overload. So what happens if you have something like this? Number and number, whatever, and then find n. Okay? The code that I'm writing, it's not real code, right? Because can you tell me why it's not real code? What is wrong with the code that I wrote so far? Yes, please.
With the find, it doesn't actually return anything. It doesn't say if it returns anything, and it's also not listed as public or private or anything.
Well, this is let's say it returns void, right? And access modifier is irrelevant. I just give it, but if you want, let's make it public. That's not gonna change much. Or we can make find return an int if that makes more sense, because find is finding something. So let's assume it returns some integer. All right. Yes, please.
Is the function find returns an int, you're not storing it?
Okay. That's a very good observation. So find returns an int. I'm not using this value. Is it okay or is it not? Do I have to put something like this, or will it work? This particular aspect will be fine even the way it was before. Say it again? Exactly. So the thing is, you are not obliged to use the return value of So yeah, you can store it in a variable like that, but you don't have to. If you do just this, then whatever int find returns, so which is going to throw out, and that would be it. Exactly, right? To the point. See how it is declared as abstract? So that means we cannot create instances of this class. All right, that's why I'm saying this is not the real code. But to demonstrate the point, let's assume that number is a concrete class, so that we can, make the point related to overloading. All right, if we have this code, right, and the compiler is trying to compile it, n is a number, and it is going to obviously decide to use this method, right? So now, what happens if we have an integer here? All right, so now it's kind of tricky, right? Because on one hand, n is a number, but on the other hand, the runtime type, right? The actual object stored in variable n is an integer, okay? So it kind of looks like, both overloaded methods would work fine, or even that this overloaded version would be better because n actually does contain an instance of an integer. All right? So, but we know that the compiler has to select just one method, right? It cannot do like, oh, I don't know, yeah, I'm torn between two options. I will decide later. Right? No, it has to, if the code was to compile, it would have to resolve to exactly one best method to call in this example. So what would it be?
Would it be number because it was defined as a number?
Exactly. So when I was giving you this description, right? So I, on purpose, right? Made some small mistakes, right? Hoping that you would notice, and you did. Right? So when we are talking about overloading, we say which method to call this decision, right? It's called overloading resolution. Is called at compile time. So at compile time, the right-hand side of this assignment is sort of completely invisible. The compiler cannot analyze what actual object is going to be stored or referenced by this variable n. Right? It is only known at runtime. Why? Well, because in this very trivial case, maybe yes, it's obvious that n would always be an integer. But what if it is, under some if? And this if depends on the input of their user. And again, this is not real code, but I'm just demonstrating the concept. All right. So what if this is something like this? And is new else and is new double. Okay. So in the general case, the compiler cannot analyze what is going to happen at runtime. What condition this condition is going to evaluate to, right? Because it may depend on things that are just not known at compile time. And that's why the compiler makes the only meaningful decision. Well, I'm never going to try to analyze the actual type of the object that will be stored in this variable. Therefore, it will only look at this. This is called the declared type, or static type of this variable, and it's going to be number. And this is the only information that will be used by a compiler when it performs overloading resolution. So yes, it will be this method, find with a number, that will be used by the compiler, right? That will be invoked by the compiler when this line of code runs. All right, so, and for this reason, right, it's only at compile time, so this is fairly easy, right? Just overloading rarely causes any issues. Unlike the second concept, which is overriding, which can be a lot trickier, right? Because overriding happens when we have a supertype and a subtype, and in a subtype, we override the method that we inherited, right? So we want to provide a different implementation, different definition for a method that we inherited from our supertype. So this method, of course, it has the same name, and you know, it might have some deviations from their you know, exact specification of their method that we are overriding, but it's, you know, those deviations are very restricted. So their parameters have to be the same. Okay, it must be so in Java. Okay, at least in Java. And then the return type can be covariant, so it can be you know, either the type of the return type from their method in the superclass, or it can be a subtype of their type of the return of the return type from the superclass. All right, so overriding is trickier because yeah, method is redefined in their subtype, and as we already mentioned, right, name and arguments remain exactly the same in Java, right? We shall see that in the general case, if we forget about the specific programming language, we actually can be a little less restrictive with respect to their arguments, right, as well. But the return type can be both in general case and in the specific Java language. It can be the same as in the method that we are overriding, or a more specific return type, meaning it can be a subtype. So if in the super type, we have find that returns a number. So let's change our example such that we have, let's say, class A, which has this find that returns a number. And then we have class B, which extends A, and now if we want an override, we have to make sure that the arguments are exactly the same. By type, right? They don't necessarily have to have the same variable name, so number I is perfectly fine, but the types have to be the same, right? And then the return type can be this number, right? It's fine, or it can be a subtype of number, for example, double, right? That is also fine. Replacing this number with any other type that is different from class A's parameters for find method would prevent the overload, would prevent the override. Right? So if we put I know, float here, it would no longer be an override, it will be an overload. Okay? So it's very important to see what you are trying to do. Are you trying to overload, or are you trying to override? And the thing is, right, the problem, little slight problem here is that, well, what if we actually wanted to override, and just by mistake, instead of writing number here, I wrote float. This code would still compile, but instead of overriding a find that I inherited from my superclass A, it will create an overload. And let's say the compiler wouldn't know what my intention was, right? So it wouldn't help me, by giving me a warning. So a useful hint here is to use an @override annotation that would tell the compiler that, hey, compiler, I am trying to do an override here. So if you notice that you cannot do override, do not do overload, right? Just give me an error. So this code now would not compile, and it would give me an error saying that I'm not overriding because parameters are different. So that would tell me that, oh yeah, I'm not overriding, I accidentally overloading, so I will fix this error, I will write my code like that, and now it is going to compile.
So to make sure the types of the arguments need to be exactly the same, but the type of the return value can be the same or a subclass.
Exactly. Yeah.
Okay.
It cannot be a super type. So if I replace this with object, no, that's not good, right? It's not going to work. So it has to be the same type that is number or a subtype. Yeah.
Is it possible to both override and overload, or does that
No.
mess up the purpose of overriding?
No, it's just simply not going to be possible because by definition, overloading is when parameters are different. And overriding requires that parameters are exactly the same. So they're,
If you inherit it from like another class, like this example from lens 5 to 8, and then you change the parameters, and it would be overriding it with no longer. Sorry, it would be overloading and not be overriding.
yes, so if you do something like this, and of course you would have to ditch this at override protection to make it compile, then it's going to be overloading, and it's not going to be overriding. So no, you cannot accidentally override and overload with the same method. Of course, you can have overloading and overriding together. So for example, you can totally have let's do public and number and number find and number n. Right, so you can totally have this, right? So you can override this find with a number, and then you can make an overload in the form of a find with a float, right? So that you can do, all right? But you cannot with a single method, right? You cannot do both an override and an overload, right? Any given method that you implement is going to be either an override or an overload or none of those, right? Of course, you can just introduce a brand new method which would not be either overloading or overriding anything. Does that make sense?
A little bit. The thing where I confuse it is where it says you can overload within the same class, right? But if you inherit from another class and you change the parameters, that is still overloading.
Okay, that's actually an excellent point. Let's imagine we don't have this thing. All right, so now I'm asking all of you, how many find methods does class A have? And the answer is 1, pretty straightforward. How many find methods does class B have? It has 2. We don't see it well, but it has 2. All right, one that it inherits from A, find with a number, and another one which is introduced in class B itself. It's not an override, it's an overload, right? But it's an overloaded find method. So yeah, find with a float. Okay. So we typically so we would say B find with a number and B find with a float. All right. So this is a notation that we it's not Java syntax, but it's just a notation for us to remember which methods we actually have. Right. So this is what we currently have, and yeah, if we want to then override this find that we inherited, we can. Right. So that would be this, for example, and of course, yeah, we need to have implementations if we are overloading or overriding, right? Because those methods are not abstract, right? But we are concentrating now not on the implementation, but on their specification, right? On their parameters and their return type, right? So yeah, and you cannot override the same method in the same class more than once, right? So no, you would not be able to do something like that. All right, because what that would mean is, oh, we are trying to have overload, which is, two overloaded find methods, which on a different return type. So no, that's not allowed, and it kind of makes no sense, right? Why would you want to override, this b.find number that we inherited from a.find number more than once, right? Because then what is compiler supposed to do? Which, how would it decide which method to call? So no, this is not legal, right? You cannot do this. But overloading, you can create as many overloaded versions as you want, right? So you can, do this, right? Right, that would be an overloaded find, right? Because it has different, a different parameter there. And of course, there are no restrictions on the return type, so you can make this object or string or anything else, right? When you're not overriding, the return type can be anything, right? With overloading, the return type can be absolutely anything. But if you are overriding, then of course you have to follow the rule that the return type is the same as in the method you inherited, or a subtype. Well, so let's do this extends B. So now, which methods? And let me get rid of this. All right. So how many find methods does class C have? Yes, please.
I feel like, let's see, B extends A.
Say it again?
Yeah, oh, sorry, I was just double checking. I feel like it has 3 methods.
Yep, it has 3 methods. One that class B inherited from class A and never overrode, right? Then, of course, class C inherits it. And then the 2 overloaded versions of find that B defined and C inherits them as well. Right? So again, you do not need to write the methods that you inherited, right? In fact, that would not be valid Java code. But if you find it, like when you're solving, next quiz, you'll find it helpful to list all the methods that each class has, list explicitly, right? So that you, when you have this chain of inheritance, you don't lose any of the methods. So that all right, yeah, I see. Class C has these 3 methods.
I just want to make sure I have this right. In the override, the argument, the return type can be a child, but the argument can't.
Yes, the arguments have to be exactly the same.
So the argument would have to be numbered, even though float is a child of number, it doesn't. That makes it not.
Yeah. So this is not an override. This is an overload because for an override, find must have number as the argument.
Okay.
All right. Yeah, that's why electronic quiz. If you're not writing, Java code that will be actually compiled and run, it might be helpful to list these methods here as if they were defined here, just to remind yourself that class C does have these methods, right, through inheritance. All right, and now let's see. We need to make another important definition, which is called method family. Method family. Method family is all the methods with the same name and parameter types. Okay, this is the definition. So, what are method families that we have in class C? Well, we have 3 method families. Right? We have find with a number, find with a float, find with an integer. All right, we have these three method families. Right. So, in class B, how many method families do we have? Same, we have three method families. Find number that we inherited from A, find with a float, find with an integer. All right, so what if in class C, we do the following. We do public and string and find and integer and then some implementation. And then we have public and integer and find and number n. All right. So now, how many method families do we have in class C? And the answer doesn't change. We still have three. We have find with a number that we inherited through class B, but originally, right, initially from class A, and then we overrode it. And that's why, yes, this is an override, so we can help us avoid errors by telling the compiler that, yes, here we meant to do an override. And then this is the first method family, find with a number. Then we inherited find with a float from B, so that's the second method family. And then we inherited a find with an integer, and we overrode it. Okay. Again, if you don't add this at override annotation, it will still be an override. Okay. But if you add this at override annotation, it helps you ensure that either this is really an override or your code wouldn't compile, right? It would not allow the compiler to compile this code if you accidentally messed up the arguments and it turns out to be an overload instead of an override. All right, yeah, still three method families. So now, hopefully, you are able to see why it is called a method family, right? Because we have, family implies that we may have more than one member, and indeed, with the method family find number, we have two methods, right? It's the same family, but there are two methods. One that contains the implementation given in class A, and another one that contains the implementation given in class C. So one method family, two methods. Same with find that takes an integer, right? Here and here, two different implementations, so two different methods, but it is the same method family. So there are two methods in the method family of find that takes an integer. It is very helpful to use different colors to mark different method families. Right, so yeah, I cannot do this easily in text editor. Right, but if you are on a quiz or on an exam and you have highlighters, feel free to do just this. Right, so you have green method family, find that takes a float. Okay, and then you have blue method family, right? Find that takes an integer, right? And this would be the same method family, blue, right? And then you have a find that takes a number, I don't know, this color, and that would be this method family. So highlight method families using different colors so that you can easier see them. And again, if a method is not overridden, but it's inherited, right? It is helpful to, just for the purposes of an exercise, to copy it to the class where it is. Right? So find is never overridden in C, in class C, but it is there. Class C does have find with a float because it inherited it from class B. So you can, to make it easier for you to remember that C has three methods, you can copy it here. And you can do the same with B to help you see that, yeah, this find that takes a number is inherited from A to B, so there are three method families. All right, so yeah, that's that. And why method family? the term method family. Why it is important? Because it helps you understand how overriding resolution works. All right, so let's go back to our slides overriding, right? Again, to sum up, basically we are providing a different implementation in their subclass. Their method name and arguments have to be exactly the same, and of course the definition, right, the implementation of the method may be different, right? That's the whole purpose that we are overriding it. Return types support covariant types. Remember, covariance meaning you can provide a subclass in place of the superclass. All right, so return types can be subclasses of the original return type in the method that you have overridden. All right, so this is the thing. Right, this last bullet point tells us why things are so complicated with overriding. Because which method exactly to call is determined at the runtime. That is the actual type of the object that a variable contains, or a variable refers, matters. But it's even more complicated than that, because it's a two-stage process. First, your code is compiled, and then your code is run. So when the compiler compiles a code, it needs to have at least some idea of the method that needs to be invoked. Maybe not down to their exact method, but at least a general idea. And this is where the definition of a method family comes into play. So let's go back to our example. Imagine, let's rework our example here. So let's do float, for example. All right, and we are calling find with an N. All right, so when compiler compiles this code, it it only excuse me, it only sees the compile time, right? The statically defined type of this variable n. So it selects the method family based on this compile time type, right? And this is an important observation. So the compiler decides which method family is going to be used for a particular invocation. So if it decides, all right, based on their use, right, n is of type number, right, and of course we need to, right, it's an instance method. Okay, so make our example. Now things are, things start to matter more. So let's say we have n dot. Okay, so that well, not n dot. Let's create an instance a. Right, we have an a here. All right, so. Now, the compiler is trying to find a suitable method family based off of their compile time type of their instance variable on which the method is invoked. The method is invoked off the find method of the a variable. The type of a is a, right? Capital A, and capital A has only one method, find. Okay, so that means that. This method family is going to be used, okay? Then A is an A, all right? So runtime, the runtime object, the runtime type of A, variable A, is the same as a compile method. So this method will be called find with a number. So now, what changes if we do this? If now variable of type A contains a reference to object C, is that valid at all? Yes, because C is a subtype of A. Okay, so yeah, this is valid. Now let's again look at the compilation of this line. A is an A, which means that the compiler will only be selecting among one method family, this one, right? Which in our example was was this pink color, whatever that reddish color is, and that means that it selects this method family, and once the compiler selects a method family, it will never ever go with another method family, right? It will not switch method families at runtime. It will only select maybe a more suitable method within the method family at runtime. But the method family determined at the compile time is never going to change. All right, so it is going to be this ping method family, and now the compiler is at runtime. Their JVM is looking at this call, and it's like, oh, but A is actually a C object, so it's going to go to the C class definition and see if there is another implementation of this method in that chosen method family, and sure thing there is. So their answer would be for this piece of code, this find method is going to be invoked, right? Because it is the same method family, but it is overridden in class C, and A variable lowercase a is actually of type C. Okay, that tells us that it's a two-stage process. At compile time, method family is determined. At runtime, an implementation, right, the specific method within the method family is determined. Of course, the result may be different if we are dealing with a method family with more than one method in that family. Right? So here we have two, right? Find number and find number. There are two methods in this family. For example, this float, find with a float, this entire method family consists of only one method. So no matter what, this method is going to be called. All right, then of course there is this added consideration that parameter types do not have to match exactly. For example, let's change this into a double. All right, and let's start with this. So an A is an A. We're trying to call find with a double. A does not have a find with a double. Does it mean that your code fails to compile? No, because we can't assign a double object to a variable of type n. So you can almost imagine that there is this invisible assignment, right? That happens here, right? And D is a double, right? But double is a stop type of number, so this assignment is valid, and therefore this method family is going to be selected. All right. So what method is going to be actually called at runtime? Well, that same method, right? Because A is an A, there's no other option. So now let's change it to C and see if that changes anything. Again, compile time and our analysis stays the same. This method is going to be selected because it is compatible, right? We can make it work, and there's only one method family. But then, since A is a C, right, the runtime environment will use this method. Right? So this method will be used when we call a.findD. Okay? So now things are getting even more interesting. What if we have
I think it's gonna stay the same because it's only gonna grab the methods that are in A, but it can't access the stuff that are specific to C, I think, so it's gonna end up just grabbing the same number one and two.
Exactly, right? And that is a very subtle, subtle observation, right? Our analysis doesn't change. Why? Well, because at compile time, right? The compiler only sees that A is an A, right? So it will look for suitable method families in class A only. Will only find one method family. And once the compiler makes up its mind on the method family, nothing is going to change it. Right? This find with a double is a different method family. Okay? And therefore, it's not going to be even considered. Right? At runtime, their choice will be between this find with a number and this find with a number. And of course, this find with a number will be invoked because it is in class C, and A is actually the C object. All right. So it might, seem counterintuitive because, like, oh, wouldn't that be a better fit for the method we're trying to invoke, right? Because D is a double, but no, method family will never be changed after compilation is successful. And we're going to see why, right? So that it's not just an arbitrary rule made up, by angry Java gods, right? You can see that, well, it would not be a safe bet invoking this find with a double, because it may exist, but it is not guaranteed to exist. What if we didn't override it? Okay? Then it wouldn't be a viable option to call. Whereas find a number, this find number that is being invoked, right? We are guaranteed that there is some suitable find with a number that we will call, no matter what their actual runtime object is. Whether it's an A or a B or a C, all of them are going to have find with a number, either inherited and not changed, or inherited and overridden, right? But all descendants of class A are guaranteed to have find with a number. Whereas find with a double, no, it's not guaranteed that any of them have this find with double. So it would not be safe to compile the code, trying to call find with a double because it may not even exist.
Wait, so just double check. When you call find D, A dot find D, is that's grabbing the find number n in class C?
Say that again, please.
When you call A dot find D, that's calling on the dot find that returns a. Is it calling on the dot find that'll return a number?
Yeah, it will return. It will return an integer. No, it will return an integer.
I'm sorry, I meant it'll return an integer.
Yeah.
Quick question. Okay, so if you set like a superpaths object to like a subpath, so like A to C, so does that mean you can only run methods that are like overridden in that subpath? You said that you can.
Well, you can only call methods that exist in their in the class that is the run that is the compile time type of your variable. So let's say we have another completely unrelated F1. Okay. Can we call F1? No. Right? This code would not compile, right? Because at compile time, we don't see what the actual runtime type of A is. We cannot guarantee that A will be C, right? We only can guarantee that A is an A, okay? And A does not have F1, so an attempt to call F1 would fail because there's no guarantee that all subclasses of A have F1 defined.
So the function, the methods that you call, it has to like be in some part in the original superclass.
In the class that corresponds to their compile time type of the variable. Okay. Right. So if we want to, call F1, well, first we could just say C equals C, and then it would be fine to call C dot F1, of course, right? Or if I still want to do this with an A, right? I can actually cast my A to C. All right, so I can, make this cast, basically convert their type of reference A to class C. Okay, but the compiler requires that I do this explicitly, right? Because the compiler knows that it may not be safe, right? It may work if A isn't in a C, but it's not guaranteed to work. So the compiler doesn't want that responsibility, so it pushes this responsibility on you, on us, on the developers, right? So if I am absolutely sure that A has a reference to object C, I can write this cast, all right? And if I was right and A is indeed a C, this code is going to work. But if I was wrong, and we had something like this, then this code would compile fine, but it will fail at runtime, giving me a proverbial class cast exception, right? Meaning that, hey, dude, you guarantee that it's going to work, right? But you failed, so here's your class cast exception.
So, if double is, double is the child of number, will line 72 run it as if it is a number? Like a polymorphism with a parameter.
All right, so here, no, it will run this C fine with a number, right? So it will be this method that is going to be invoked here. Will evoke this fine, right? Because there is, right, because the declared type of A is A, right? So there is no guarantee that A, let's change it back to what it was, so that, right? So there's no guarantee that A is a C, right? A can be an A can be a B, A can be a C, right? And that means we cannot afford calling double here, because double does not, find with double does not exist in B, does not exist in A. So the only safe bet is to call find with a number, but of course if there is an overridden, better suited, more specific implementation of this find with a number in class C, of course we would want to call that one.
Yeah, and so it works even though the parameter is number and you're passing in a double?
Yes, because of this, right? So if we have a double object, we can assign that object to a variable of type number, right? Because double is a subtype of number, okay? So here, right, the argument is number, and we can imagine that this assignment would be valid.
If you change the left-hand side typing of A to C, right?
Ah, interesting.
Which of the two does it call?
Let's try this one. All right, so now the runtime type of A is C. The compile time type of A is also C. All right, and then the compiler here is looking at all the methods in class C, and it is finding the best match. And of course, this would be the best match. So here it would call C find that takes a double.
Is the best match is the most specific?
Yes, it always tries to match their arguments exactly, and if that is not possible, then it tries to see if the match is possible at all, right? Because if we call something like, let's say, let's do this, A find new object, okay? So which method would be invoked here? Or is it not going to compile?
what sort of applications would you use something like this for? Like making like setting a superclass object to like a subclass reference?
Yeah, so the practical importance of this is that when you're overriding, right, you want to know exactly, what you can do, right, and you want to know exactly which method is going to be invoked, so that you do not accidentally invoke not the method that you wanted. Right, that's why it's important. So, how about this? Right, this line. Yes, please.
I don't believe it will compile because object is less specific than.
Yeah. Exactly. So, we are going over all methods defined in C, right? And we're trying to see if any of them is going to match. Right? Can we assign an object to I? No. Right? Can we assign an object to number? No. Can we assign a number to double? No. So this is not going to compile exactly.
So I guess is it like you want to like you want an object that you know will only run functions from the original superclass, but with the sort of like differences in like the way it's overridden in the subclass?
The idea here is that when you are overriding, you're providing an implementation that is better suited for a specific class. So you're replacing the implementation that you inherited. When you are overloading, you're providing a greater range of method families that would be able to take different types of arguments. Okay? But the implementations may be completely unrelated. All right, so back to our slides. All right, so what we are seeing here is called subtype polymorphism. All right, this is their ability to use a subclass where a superclass is expected. Java uses dynamic binding by default with certain exceptions, but unlike C++, where you have to use the virtual keyword, in Java there is no need for it. So all methods in C++ terminology, all methods in Java are virtual by default. Okay, so it just Java terminology is not using word virtual, right? In Java, we do not call them virtual methods. We call them methods with dynamic method binding. Okay, but the concept is exactly the same. Right? The implementation slightly differs, but the concept is exactly the same. All right, so we have, and we've done an example already. All right, so here's M, and it's overridden in their subtype, and it's overridden in the subtype. So when we have A.A, and then we call M from A, right? It's the same method family. So any of these three methods M can eventually be invoked. Which one exactly depends on their object that is actually stored in this variable lowercase a. Right? If A is an A, it's going to call this M. If A is referring to object B, it's going to call this M. If A is referring to object C, it's going to call this one. Polymorphism is essential because it is very instrumental. It is extremely helpful when you're trying to reuse code, when you're trying to write code that can be used with a variety of objects, right? Yeah, I want my code to work with cats and dogs and frogs and all the animals, right? So this is generalization, right? So you are trying to avoid having to write three slightly different implementations for each of the animals, right? If you are able to capture the similarities between these, all the animals and write just a simple method that works equally well with whatever the type of animal you are given, of course, this makes a very concise and robust implementation. All right, so this is an essential feature, as we shall see in one of our last topics on design patterns. A lot of, probably the majority, or at least a great deal of design patterns are based on subtype polymorphism. All right, so Java subtype, we have already seen how it works. The syntax is class B extends A. If we are talking about extending an interface, it's not really called extending in Java terminology, it's called implementing. So class B implements I. Implements is a keyword. All right, and Java subtype is not necessarily a true subtype. So we haven't given a definition for the true subtype. We will shortly. All right, but Java subtype we know, right? When we extend another class or when we implement an interface, we are creating a subtype. All right, so let's look at more examples. We have different shapes, circles, squares, and we have shape type, which kind of tries to capture them all. What if we want to kind of sketch an application that draws shapes on the screen? Here's what a typical C-style solution would look like. We would define an enumeration shape type where we would list all the possible shapes. Then we would define a shape struct, and then we would define specific structs for each of the shapes, like circle, square, and so forth. Right? And then we would have the shape type to indicate the type of the shape, and then whatever parameters are needed to define the specific shape. Right? So for circle, it's radius and center. For square, it's side and top left, and so forth. All right. So what would then our code be, again, in plain old C, to draw all shapes from an array of shapes, right? So here's an array of pointers to shape, right? And we want to have this universal method that draws all the shapes, any shapes, in the array, right? Because we know that all shapes can be drawn, right? So what we would have to do is we would have to analyze the specific type of the first element of our struct, the shape type, and depending on whether this T is a circle or a square, invoke a different method. Okay? So yeah, we cannot, even if the code for drawing a square is very similar or even exactly the same as draw a circle, we cannot, we would still have to have two methods, draw a circle, draw a square. Right? We cannot capture the similarity between the shapes, and of course this is not good. So we want an object-oriented approach. Right? So that was C, plain old C. So no object-oriented anything. But in an object-oriented language, we want to capture the fact that all shapes have a draw method, and we are calling draw all. We just need to call draw on every object that we are iterating over. Okay? And then, of course, these draw methods can be the same or can be different. It doesn't matter. Our draw all method is universal. Right? It works for all possible shapes. And the guarantee that it does work for all possible shapes is that our class shape defines the method draw. Right? Class shape is an abstract. And abstract keyword is skipped here, but it is actually required, right? So this draw method is also abstract, which means, yeah, there is no implementation for draw in shape, mainly because we cannot come up with an exactly the same implementation of draw that would work equally well for all shapes. That's why we defer the implementation of draw to more specific classes, so that this draw will know how to draw the circle, this draw will know how to draw the square. But the idea is, it is the same method, it's just a more specific implementation. So you see, we define draw, we declare draw in shape, and then we overrode the draw in circle and square. But since it's an override, the method name is the same, right? We no longer have to do any kind of conditional logic, right? And this code works equally well. So, what is the benefit of this approach? Remember, we mentioned it earlier, it's open-closed principle, right? One of our most beloved principles. So open for extension and closed for modification, which means extending existing code should be relatively easy and does not require modifying a lot of the code that was written previously. Right? So, starting with this example, or continuing with this example, what happens if we want to add another shape, triangle, right? So, in our C implementation, we would have to add comma circle here, a comma triangle here. We would have to define and use struct circle, which would be, shape type T, and then, let's say, 3 angles of the triangle, or whatever parameters we decide to use as our representation. Thank you. And then here we would have to add another line in this switch. Right? A lot of changes. Right? Clearly not following their open-close principle. So now let's see what it would this change, what it would entail in the case of Java. Right? We just have to implement our triangle. Right? Declare we now have a triangle class. Implement its draw. Draw all does not change a single character. Right? So it just works for all future shapes that we may add in the future. All right, so this is great for extensibility and reuse, right? We reuse this draw all for all current and even all future yet unknown shapes, right? So this is, as I mentioned, open-closed principle, and a lot of design patterns are based on similar ideas, right? So design patterns, which is our topic after we're done with Generis, is going to be about those recipes for good design, right? So best practices, how to write the code, maximizing extensibility and reuse. All right, so now let's talk more about this true subtyping that we briefly mentioned earlier when we said that Java subtypes are not true subtypes. Okay, so what is a subtype to begin with? Well, a subtype is a subset, right? So, for example, integer is a subset of number. Range from 0 to 10 is a subrange or subtype of range of -10 to 10, and there are many other similar examples, right? Book is a library, activity is a library, triangle is a shape, and so forth. So what is true subtyping? True subtyping is such subtyping when certain conditions are met. First, so here's the definition. B is a true subtype of A where every B is an A without exceptions. So it's an is-and relationship, right? So is an A. Every B is an A. So every array list is a list. Okay? In other words, right, it's all about substitutability. So every B is an A means that we can replace any object A with object B. Right? So object B can be substituted in place of an object A. If this is true, right, if this holds, it is a true subtype. So subtypes are basically substitutable for their supertypes. And that, of course, means that instances of subtypes, they should not surprise the client by requiring more. So they should not have a stronger precondition, and they cannot offer a weaker post condition. They should not surprise the client by returning less, right, in the post condition. This is the definition of true subtyping. Java subtyping is implemented as subclassing, right? So when we say class A extends class B, right? Class A is a subclass of class B. This is the way Java implements subtyping. But it is extremely important to see here, to note here, that Java subclasses are not the same as true subtypes. Okay? Here is their contrast. So, subtyping and substitutability, they are specification notions. Right? So, B is a subtype of A. Excuse me, folks. Up there, folks. Can you please keep it down? I paused like 3 times. And you're not even looking at me. You're very busy and you're talking very loudly. Would you please keep it quiet? So B is a subtype of A if and only if the B object can be substituted in all the circumstances where an A object is expected. It's important to to underline here in any context, okay, regardless of anything. So this subtyping and substitutability are about specifications, whereas subclassing and inheritance, it is specific to the programming language. Those are implementation notions, right? B extends A, B implements A. This is subclassing, right? And of course, it only makes sense in the presence of inheritance, right? So in Java, we cannot create a subclass without inheritance, right? There's just simply no such syntax. B extends A, meaning that B is a subclass of A, but that also creates this inheritance hierarchy, right? B is derived from A. Whereas with subtyping in general, right, as specification notions, there is no inheritance, right? So B and A can be arbitrary types, right? We're not talking about inheritance at all, right? It's only about the capabilities of these 2 types, B and A, right? The methods that they have, right? There is no notion of inheritance because it's a specification notion. All right, that's pretty much it, right? Subtyping is about substitution. B is a subtype of A if and only if an object of type B can be substituted for an object of type A in any context, whereas subclassing is the specific implementation of subtyping in a programming language. It depends on the implementation of a particular language, and it is closely tied to inheritance, right? So it is the mechanism for which the subclass inherits the methods from their superclass, and then has an option of replacing their implementation without changing the type specification. All right. Once again, true subtyping. We say that class B is a true subtype of A if B can be substituted for an A in all the contexts, and more specifically, right, we are going to need a better definition, right? Because can be or cannot be substituted is a little vague, so we need a better tests to check if something is a true subtype of something else or not. So here is the requirements that you can just apply directly. So B is a true subtype of A if B is a subclass of A and it has a stronger specification than A. And stronger specification, we already know, it means that weaker requirements and or stronger promises, stronger results. All right, so that's that. And yeah, Java subtypes are not true subtypes, and not necessarily so. But it's on you to decide whether you want your Java subtypes as true subtypes or not. If you make Java subtypes not true subtypes, the compiler is not going to stop you, right? It is legal Java code. but it's going to create problems with your inheritance hierarchies, right? So it may cause subtle bugs that would be very hard to find. So the recommendation is, and the reason why we're talking about this, kind of abstract definition of a true subtype, is that while the language itself, Java, is not going to stop you from creating subtypes in Java that are not true subtypes, you should always strive to avoiding this. You should always try making your Java subtypes true subtypes. Okay, and here is an example. All right, well, in fact, several examples. So we have interface points 2D, and we have another interface points 3D, which adds the third coordinate. So B is a subtype of A, meaning that B can always be substituted for an A. All right. So with this example, point through D can always be treated as a point to D, right? Because point through D is essentially a point to D. Point through D is a point to D with just added Z coordinate. All right. So yes, in this case, point through D is a true subtype of a point to D.
It's the way of kind of like making sure that you keep something, you make something that is a true subtype by first design, when you create, I guess, if the ADT, if you create like the design and everything, and then that's when like you check to see if it's a true subtype or not and make it so that, and then you do the code. Is that kind of how it's done?
Yeah, so basically when you are implementing your subclasses in Java, check every subclass and make sure that it's a true subtype of its Java supertype, right? Because it may be so, but it's not guaranteed by the language itself.
Wouldn't it be kind of difficult to make a subclass with a more open specification? Like, well, because if it has to extend the thing and it's getting everything from its parent anyway, I just don't really understand how that could be more open. You know what I'm saying? I feel a little confused about that.
Well, let's go over some examples, and then if we can come back to you to see if, right? If examples help to clarify this. All right. So subclassing. Okay. We have product, title, description, price, get text. And we need a class for products that are on sale. And we do this through subclassing, right? And remember, subclassing is the Java way of subtyping. So we create a sale product, and we essentially copied and most of their product code, okay? Well, this is right. So sale product is not inheriting anything from the product. And of course, it just changes, right, or provides slightly different implementations to get price and get text to account for this factor, right, or like discount amount, discount percentage. All right. So what is bad about this approach? It's very hard to maintain, right? Because what if I want to add another attribute to all my products, whether they're on sale or not? Right? For example, I don't know, category. Right? I would have to add both classes. Right? That's not good. Let's see if these two are actually true subtypes. Again, true subtyping does not require two types to be a super class and a subclass. Right? So we can totally write product and a sale product that are not inherited from each other, but that are true subtypes. Right? Because true subtyping is about behavior. All right. So we are looking at these two classes. Do they have? Can we always substitute sale product for product? Right. So imagine we had an instance of product. Can we just substitute an instance of sale product for it? And the answer is no. Why? Well, because imagine that the price, we had an object product with price 10, and get price was returning 10. If we substitute with a sale product, the same price, 10, and we call the same method get price, it's not going to return 10 because of this factor, right? So we see that if our client had a product object and called get price on it, if we, instead of this product object, give them, right, without them noticing, if we just decide to replace this product with the same product, right, given that all their attributes are the same, title, description, price, get price will not return the same value. And that means no, it's not substitutable. So no, it's not a true subtype. All right, so, and of course we can, reduce their maintenance requirement by making sale product extend product, if that helps, maybe it helps, okay? But we would then just avoid copying and pasting code. We would only have to override get price. Again, that does not make sale product a true subtype of product. It is still not, okay? Because it's not substitutable. All right, which again shows that Java subclassing does not necessarily mean that these two types are going to be true subtypes of each other. Right, but at least we were able to, and I'm going to make one step towards their open-close principle so that we, this code is easier to extend. All right, so of course there are alternatives to inheritance, as we mentioned earlier, and one of the most prominent ones is composition. Right, so instead of having sale product extend product, make sale product just a separate class, and have product as a field in sale product. All right, so benefits of subclassing, obviously we inherit fields and methods, and we can reuse them, or we can replace implementation of the methods that we are not particularly happy with. Right, the catch is that you cannot reject any of your inheritance. Right, so if you inherit certain fields and certain methods, right, with fields you cannot do anything. Right, you just have them. With methods, you can override them, but you cannot delete them. You cannot delete fields. You cannot delete methods. You inherit them. You're going to have them. Right, and that sometimes can be a problem. Right, so if you are finding yourself in a situation where you're like, oh yeah, I'm making, I have my graph class, and then I have my, super graph class, a cool graph class, which extends graph. But then I find that inheriting all those methods from graph, I kind of wish to prevent my client from calling them on the cool graph. Right, so these methods I want to sort of delete in a sense. Then it is a good sign that you're not building your inheritance hierarchy correctly. Right? If your inheritance hierarchy is correct, you shouldn't be wishing to remove some of the fields or remove some of the methods that you inherited. All right, so this subclassing in general, of course, good for maintenance. Differences are very clear, right? So they're not hindered by tons of similar code. Right here we see that things that are really different in sale product from product, and it promotes modularity, right? Because we can ignore private fields and methods of the superclass, right? Because they are not accessible in the subclass. All right, so we can substitute new implementations where the old one is expected. Right, so this is subtype polymorphism, and of course there are disadvantages. The code may break quality. Remember our problems with the duration and duration earlier, so that is one of the potential issues. So subclassing can be misused, and that means that if you do not think thoroughly about your inherited hierarchies, you might find some very subtle bugs, and an example is coming up. And if just jumping ahead, but just to give you a heads up, right? All those subtle problems you can avoid if you do not create Java subclasses which are not true subtypes. Right? So if you follow the rule, my Java subclasses should be true subtypes, then your code is safe. Your methods are substitutable. If not, then you might find yourself looking at some of the problems that we are going to discuss. And the first one is a fragile base class problem. All right? So here is a square that extends a rectangle. Okay, we are asking, is square a true subtype of rectangle? In other words, can we substitute square for rectangle in the client code? So here are set size and area methods in the rectangle. Right. So to answer this question, let's look at some choices here for how we would potentially implement set size for the square. All right. So intuitively, from geometry, you probably know that yeah, square is just a special case of rectangle where their width and height are the same. But this, this line of thinking might actually, not serve you well when we are talking about substitutability, right? Because it turns out that no, square is not substitutable for a rectangle, right? And one of the early signs of why it's not going to work is square is simpler than a rectangle, right? Rectangle is more complicated. It's a more specialized version of a square. A rectangle needs more parameters to describe it. Rectangle needs at least 2 parameters, right? Height and width. Square just needs one side.
So can you make a rectangle as a subclass of a square?
Well, you can try, and we'll see what happens. All right. So, let's first. You can, right? But whether it's a good idea or not, that's a different story. Let's look at these 4 choices for how we could implement set size. Right? If we analyze, so basically, the problem is we are inheriting too many parameters, right? We are inheriting width and height, and we don't need them, right? We only need one, like side. So we are trying, either to guarantee that width and height are always the same artificially, or we are trying not to use one of them, right? Either their width or the size or the height, so here are the specs written for each of the proposed, or we can throw an exception if width is not equal to height, right? So all of those attempts, they indicate that, yeah, we are trying to get rid of our inheritance, and that means that something's wrong. It means that we're not dealing with true subtypes, right? So why these choices are not good, right? Because choice number 1, right, clearly requires more, so it's going to break clients, right? Set size is not stronger in square, does not have a stronger spec in square than set size in rectangle, right? So yeah, that's not good. Square cannot be substituted for a rectangle, right? Choice number 4, right? It throws a new exception for values in the domain, and when we were talking about specification, we said it's no. You cannot throw in a stronger specification. You cannot throw new exceptions in the domain. Okay. So if they're not in the domain, it's okay, but no new exceptions in the domain. No, that's not good, right? That might surprise the client, right? So yes, a square definitely might cause a problem with the client if we substitute, if instead of the rectangle, we give them the square. All right, choice number 3. Could do, right? But it's not an override; it's an overload. Okay, so not so good.
Just to double check, it's that the parents, is it the the child methods can't throw new unchecked exceptions, right?
Yes. So here we are talking about set size for square and rectangle, And we want square to be substitutable for rectangle, which means set size in square must have a stronger specification. Because if it's not set size on square is not going to be substitutable for set size in rectangle, which in turn would mean that square is not substitutable for rectangle. Right? Which means it's not a true subtype.
Gotcha.
Right? So choice number 3, right? It's an overload, not an override. So yeah, that would allow a client to break their record variant when we, what they call the inherited set size method, right? Because remember, when you're doing an overload, you're not overriding. So that inherited method that you didn't override, it still exists, and the client would be able to call it. Okay? Again, you cannot just prevent the client from calling a method that you inherited, right? If it's a private, if it's a public method, right? You cannot do anything. You cannot make, when you're overriding public method, remember you cannot limit their accessibility, right? If it was public, it must stay public when you inherit it.
I know this is kind of a dumb idea, but you could overload the function to ignore the second argument.
You could, but that would still be an overload, so nothing would prevent the client. Right? The client would know nothing about your overload. Because when you do overload, you are adding new methods. And if your client is written against the rectangle, how would they know that your square has those new fancy methods?
Overload.
Hmm?
Overload it to ignore one of the arguments I get.
Well, you can, but we're talking about overloading something here in the square, right? And the client is written against rectangle, right? So the client wouldn't know about your fancy overloads in square, right? So they would know that they exist. They would know that they are supposed to call because they're written against rectangle. And the idea is we are trying to see if square is substitutable for rectangle. All right, so choice number 3, no good. Choice number 2, again, no good. And here's an example where we almost got it with choice number 2, right? Because we're not getting any weird exceptions. We're not, we are very close to accomplishing our substitutability, but alas, no luck, because when our client is written against the square, right? They expect against rectangle, right? They expect for a rectangle 5 by 4, they expect the area or the get area method to return 20. Whereas that same method, if instead of a rectangle with 5 and 4, we give them a square object with 5 and 4, even if we try to ignore that 4, right? And we say, it's only going to look at 5, right? But still, area would return 25, right? 5 squared. And it's a different value, right? It's a different value. So no, it's not a true subtype because we cannot just, in the line that is written against rectangle with 5 and 4, substitute that object with a square of 5 and expect the client to see no difference. The client will see a difference because their area method will return a different value. So no, all right. Bottom line, square is not a true subtype of rectangle, and there is nothing that should be done. So maybe, as you proposed, maybe we can make it work there in the opposite direction, right? So maybe rectangle is a true subtype of square. And if you kind of do the same exercise, you'll see that no, unfortunately, it doesn't work in the opposite direction either. So neither square is a true subtype of rectangle, nor is rectangle a true subtype of square. A little upsetting, but we have seen, yep.
So they just have zero relation at all. They have totals.
So basically, they're not substitutable for each other. Right? They have something in common. Right? It doesn't mean they have nothing in common, right? But they are not as closely related that we can substitute one for another. So what that tells us is that, well, you shouldn't be making a square in, now back to the implementation side, right? In your code, do not make square a subtype of rectangle, do not make rectangle a subtype of square. So you have to rebuild your inheritance hierarchy to not make these two types directly related by subtype. Right? They might still have some similarities, so you can do this. Right? So capture all similarities in their class, like shape, and have both square and rectangle extend to that shape. Right? That can be done. That does not make square and rectangle a subclass or superclass of each other. Okay? So yeah, that is one possible solution. All right. Much of what we have discussed is captured more formally in the list of substitution principle, LSP, due to Barbara Listow, right? So Turing Award recipient. Right? This is essentially their Nobel Prize equivalent in computer science, right? Everything, all the rules that we sort of developed by intuition, this LSP just captures formally. Right? So ensure that B is a true subtype of A by reasoning at the specification level. Forget about inheritance, right? If you're talking about substitutability, it's not necessarily about inheritance. So B should not remove methods from A, right? Again, those are all the requirements that two types, B and A, have to satisfy if we want to say B is a true subtype of A. So B should not remove any methods from A. For each method in B that substitutes a corresponding method in M, in A, B's M specification should be at least as strong or stronger than M's implementation in A. Okay? So that the client is not surprised. Right? So if the client is written like A.M, if A is an A or if A is a B, shouldn't matter, right? So the client should not notice this substitution. So any property guaranteed by the supertype must be also guaranteed by the subtype. Okay? For example, if the supertype returns area of 20, then the subtype should also return the area of 20, given that all the other properties of the object are the same. Anything provable about A has to be provable about B. If we have an instance of the subtype and it is treated exactly as the supertype, then only methods and fields of the supertype are accessible. Okay? And we have seen this in an example, right? So if we have capital A, lowercase a, then through this lowercase a variable, we can only access fields and methods that are defined in A, not any of their subclasses of A. Even if A happens to actually, at runtime, happens to refer to a variable of type B or C. Finally, functions that use pointers or references to base classes must be able to continue using those objects of derived classes without knowing that this substitution happened. All right, those were the main rules. Here are a few additional considerations. So first, contravariance and covariance. So contravariance, which by the way is not allowed in Java overrides. All right, so this is not something that you can exercise in Java. But contravariance is the ability to use super types in the parameters. Okay, that does not break the definition of true subtype. Okay, so actually some of the languages, very few languages, but there are languages that allow contravariance in overrides, just not Java. Right? In Java, when we do an override, parameters have to be the same. In languages that allow contravariance, when we are overriding, we can replace parameters with their super types. Okay, and that kind of goes in the opposite direction from what we can do with the return type. Remember, return type we can replace with a subtype. This is covariance. And parameters we can replace with a supertype. This is contravariance. And again, very important, covariance for return types you can do in Java. Contravariance for parameters you cannot do in Java, but it is in general allowed, just not in Java. So no new exceptions should be thrown unless there are subtypes of exceptions. Preconditions cannot be strengthened in the subtype because, of course, this weakens their specification. Similarly, postconditions cannot be weakened in their subtype because that also weakens their specification. All invariants must be preserved in the subtype, particularly the rep invariant, and a history constraint, so their subtype must not be mutable if supertype wasn't mutable in the same way. All right, so that's that. So given all those rules, right, if all those requirements are met, then B is a true subtype of A, and that means that B can be substituted for A in all contexts. Any property guaranteed by A must also be guaranteed by B if it's a true subtype. In particular, their rep invariant must hold, and we cannot have weaker specifications in B as compared to A. All right, so more specifically to, more specific to how to use all this magic. When we have methods in Java, right? So for each method in their supertype, the subtype may have a corresponding override method. It may, but it doesn't have to. It may also introduce new methods, just brand new method not related to anything, or overloaded methods in a subtype. It's perfectly fine. When we override a method that we inherited, we have to go with the same spec or a stronger spec, which means we should not ask anything extra from the client, right? So the precondition has to be weaker or the same, and the postconditions might be have to be stronger or the same. We may substitute supertypes as arguments in some languages. Again, this is contravariance. It's allowed in some languages, just not in Java. Okay, then when we override, we have to guarantee as much as the supertype guarantees. So the effects clause has to be at least as strict as the effects clause in the supertype. We cannot have any additional entries in the modifiers clause in the subtype because again, that would weaken the specification. And yeah, we can have covariance in return types. In other words, we can substitute the type of the return value with their subtype. No new exceptions in the domain, of course, because that would surprise the clients. All right. So yeah, this is their list of substitution principle. Right. So this meme is is referring to their duck typing, which hopefully you'll remember from your CS1 Python class, right? If it quacks like a duck, if it swings like a duck, if it looks like a duck, it's a duck. Right? That was the duck principle. And the list of substitution principles kind of change this a little, saying that if it looks like a duck, quacks like a duck, but right, it doesn't swim like a duck because it means batteries, then you probably have something wrong in your inheritance hierarchy, right? So you have the wrong abstraction. All right, so we have about 2 minutes, so let's stop here and